A2 further maths, Euler's step-by-step method. Okay, so what we're going to look at is we're going to look at a way of solving what we call first order differential equations. This might be the first time you've heard the words differential equations and first order. So what I'll just do is I'll explain what these are. So you've seen equations like this before. Okay, so you can see this is a gradient function. You've seen that quite early on in year one. And so what that is, written on its own, is what's called a differential equation. Okay, so a differential equation is basically when you've seen dy over dx equals something. The first order means it's the just dy over dx. Okay, it's the first gradient function. As you know, you can find the second derivative. That's a second order differential equation. So when you do d squared y over dx squared, and you look at the nature of the stationary points, things like in the first year, what you're doing there is you're looking at a second order differential equation. Now what Euler's step-by-step method does is it allows you to solve first order differential equations. Let's see how it does it. So if I've got this equation just here, what I'd like you to do please is before we start looking at Euler's method, just see if you can find out the y value for me please. So someone said to you, that's my gradient function, what's my equation? Alright, so just pause, have a quick go at that. Okay, so you'd be absolutely spot on if you integrated it. You integrated it, don't forget the plus c. We don't know what the c value is, but we have been given this extra bit of information, so hopefully you spotted that when x equals 0, the y value also equals 0. So when x equals 0, this part is going to equal 0. So I can use that fact, and therefore I get the equation y equals x cubed minus 4x squared plus 4x. Now the issue you might have is having an equation that you can't differentiate very easily. Alright, integrate very easily. So if you can't integrate it very easily, then you might need to have an alternative way of being able to solve the differential equation and be able to figure out the y values at certain points. So the way we do that is by using Euler's method. Now for this one, it's fine. We can be able to factorize it, we can be able to sketch it, that's what our graph's going to look like. But let's just for argument's sake, pretend we couldn't integrate this. And we're going to see that Euler's method can be used to approximate these values on this curve. So for example, if I said, what's the y value when x equals 1, how would you use the differential equation to be able to do that if you couldn't actually integrate it? Now we know the answer is 1, but we need a method to be able to do that if we couldn't integrate. And that's what Euler's step-by-step method does. Euler's step-by-step method, grab your notebooks then please. Just that one box. So Euler's step-by-step method can be used to find approximate solutions. It's not perfect. It's a numerical technique for solving first order differential equations. Finding the y values if all you have is a gradient equation. Okay, and it can be done by knowing what the gradient function actually does. Okay, as soon as we know the gradient function basically finds the gradient, points us in the right direction of what we should be traveling, because we know that, that's what the gradient function does, that's what the Euler's step-by-step method does to approximate the curve. And if we keep using it over and over again, it should also give us a very good approximation on what the graph looks like as well. So say for example we had the gradient function, but we want to know what the original graph looks like. Euler's step-by-step method is very handy at being able to sketch out what the graph looks like. Right, so what we're going to do is we're going to just work through how it works, and then I'm going to give you the formula and show you one that you're more likely to get in your exam. All right, but it's important to make sure you understand how the Euler's step-by-step method actually works. So we're always given us some sort of starting value, some sort of point that we know is on our curve. Without that point, we wouldn't know whereabouts to start. It could be absolutely anywhere. So we do need a starting position, something that works in this function. But that's all we know. We don't know anything else about this original function. The other thing we know about the function, though, is what its gradient equation looks like. Its first order differential equation. All right, we know that's what the gradient function looks like. Now, because we know that, we should have some idea on the gradient at that point just there. And that's what we're going to work out. We're going to work out the gradient of the curve at that point. And if we know what the gradient of the curve looks like, we know basically what direction it's traveling at that point. So what I'm going to do is I'm going to stick 0, which is the x value. All right, it's the first x value. There it is. F of x is 0, so x equals 0. So we're going to put the x value in here, and I know that the gradient at that point is going to be 4. So at that point, I know that it's going up with a gradient of 4. Now, I don't know what's going to happen straight away. For all I know, after it's gone 4, it's going to curve down here. It could curve up here. It might stick at that gradient equals 4. I don't know. All right, but what I do know is at that single point just there, its gradient equals 4. So what I can do is I know it's traveling roughly in that direction. Okay, at 0.1, it's gone up to about 0.4. Yes, it might be curving off. All right, but I just know at that point that's the general direction. So what I'm going to do is I'm going to travel in that general direction for a certain amount. Now that certain amount is what I can decide, or what the examiner would actually tell you. That the step size, the step-by-step method, so the step size is dictated to you. And in this case, I'm going to just choose a step of 0.2. So the step between each of my particular x values is called h, and you will be told what that is. Now I'm telling you that my first h value that I'm going to look at, my step size is 0.2. So what does that mean? Well, it means that I know at that point I'm travelling at a gradient of 4, and I can stop when I reach the end of this first step size, and then I can investigate it again and I can find the gradient at this new point. That's what I'm going to do. So I know I'm travelling that direction, so I travel up to get to my next point, the step size. Now how we do that, right, how we actually calculate it, it's quite easy to do on the graph. Yes, you could get a ruler, you could just draw it and you stop there because that's where 0.2 is. But what does it mean numerically? Let's just have a look. So we know that dy over dx means the changing up over the change in the along. Okay, it's up over along. We know that. So what I'm going to do is I'm going to rearrange this equation. If I want to know what the change in the y value is, I can multiply by the change in the x on this side. So I'm rearranging and I'm saying, what's my new y value going to be? Okay, it was down here at 0. What's my new y value going to be? Well, how do I work it out? Well, I know the gradient. Okay, that's the dy over dx. I can work that out at whatever x value I'm investigating. In this case, it's x equals 0 because it's the first one, times by my change in the x. Now that is what's been dictated to me. I know that the change in the x is my step size of 0.2. So look at the rearrangement. What's my change in my y value? It's 0.2 because that's the x. I'm timesing by that, times by the gradient at whatever x value I'm dealing with. And this first one was the gradient of the previous bit, so it's gradient of 4. So therefore 0.2 times 4, which is 0.8, which makes sense. That's my gradient of 4 stopping when I reach 0.2. Right, once I get to that point, I don't know what this graph's done. I don't know whether it's been going down like this. I don't know, something like this. It might be very good. It might be a really good approximation. So what I do is I need to stop and investigate it further. I need to look at the gradient of the graph at this point. And that's what I'm going to do next. So yes, gives us an approximation of 0.2. We've got a new point, which I'm going to work with. And I'm going to work out the gradient at 0.2. So there we go. I put 0.2 into there, put 0.2 into there. I work out my gradient. I know now that at that point, my gradient is 2.52. What I don't know is whether that point is correct. It might be down here, it might be up here. Okay, I don't know that. All right, if it's curving off, maybe it's further down here. All I know is at that point, wherever it may be, it's going off in this direction. Okay, with a gradient of 2.52, it's decreased its gradient. Right, so can I work out where my new y value is going to be without just getting my ruler and plotting it somewhere up here? How do I do it? I do the same technique as before. I do 0.2 times by the gradient at point at the previous point, which is 2.52, and I get 0.504, but I have to be careful because that isn't going to be our y value, of course. Our y value, our new y value, is up here. It's about 1.3, isn't it, if you look at it? It's clearly not 0.504, so I need to be very careful. To get my new y value, I don't just use this equation. I've always got to add what my previous height was. So in the previous one, I had 0.8. So my new height is going to be the 0.8 plus this 0.504. So that's starting to form this equation. To get my next y value, to get my next height, it's going to be the previous height, which I can see there, plus the step size, the x value, times by the gradient at the previous x value. Okay, and that's starting to show where an equation is coming from. To work out my new y value, I just do previous y value plus 0.2 step size times by the gradient equation with the previous x in. And I can follow that. I can keep doing that same technique. All right, so yes, add those two together, 1.3 over 4. We can just see where that's come from. Perfect. Right, so what do I do now? I can take my new value, okay, which is going to be 1.304 when x equaled 0.4, and I can work out the gradient at that point, and then I can work out the step size, or I know the step size is 0.2, and so therefore I can work out the next value. So the previous value, 1.304, plus 0.2 times the previous gradient. All right, so the gradient at this point. Now the gradient at this point will be me substituting in 0.6 into there to see what I get. And it's 1.556. And so my curve is starting to get, I can see that my curve is something like this sort of shape. Right, just jump forward a bit, 1.56 plus 0.2 times the gradient at 0.8 and so on. Okay, so just double check some of these figures, make sure you're happy where they're coming from. But notice it is an iterative approach because you're always using some previous information. So there we go, 1.52 times 0.2 times 1, that's why it's exactly 0.2, 1.32 and so on. Okay, so 0.2 times that, and there we go. All right, last one, 1.6. So I've done quite a few extra points there, and you probably thought it was a bit overkill. But the reason why I did those extra points is just to show you what that shape of the graph looks like. Okay. One thing I can't say though is the graph is actually going to be completely correct, or is it going to be completely off? All I know is the shape of the graph is probably about like that. Okay. The actual graph itself, if I drew it on, looks like this. Okay, so the actual graph looks like that, and you can see that the shape is very, very good approximation. Okay, right, so the question is how could I prove that approximation? What could I do? If I wanted to improve it, I wanted to get close to this curve just here, what could I do to improve it? Okay, so just pause until you got the thought answer. Right, if you said it decreasing the size of the step, so instead of going from 0.2, 0.2, 0.2, going to say 0.1, then you'll be right. Decreasing the size of the step does improve the approximation on the curve. So let's have a look at what we would have got if I'd done 0.1. So if I'd done the actual step of 0.1, so that's only half better. Look at the difference in the graph I would have got. Okay, each of those steps. So it's still higher than it should have been, but the actual approximation is a lot better. And the more you cut the step size down, okay, maybe I could have tried 0.01, then I would have had a very, very good approximation because you're checking the gradient at really, really close points. Okay, it's just going to be too time consuming to be able to do it like that. Okay, so grab your notebooks then. So Euler's method finds numerical solutions for differential equations. So we've seen the theory behind it. We've seen how Euler's step-by-step method works. But generally in your exam, you'll be just expected to solve a question. So let's have a quick look at the formulas first, and then we'll have a look at a question. So if we're given a first order differential equation equaling some function of x. It could be any sort of function of x we like. Okay, and we're also given a step size, so we know how much we're going to be stepping up by in the Euler step-by-step method. We're also given an initial starting point, some point that lies on our curve that we know that we can actually start from, because without that, there's not much we could do. And we want to form a reoccurrence relationship. So because we know this point, we're going to be looking at the next point along. Now the x naught is just going to be the next x along will be plus a h, and then plus another h for the next x, plus h for the next x, and so on. So that x value is just increasing by h each time. It's the y value that we need to figure out, remembering that we don't have a y equals equation. So the formula looks like this. The y value is going to equal the previous y value plus the step size times by the gradient of xn, so the function f of n. Now notice that that function there is the gradient function. Some people get a bit confused thinking that this is the original function. It's not. The way it's written is like this. The first order differential equation is f of x. Okay, you're never dealing with the original function. You never integrate this, so you're never actually dealing with the y equals equation. You're only dealing with a differential equation. So they call it f of x, not f dash of x or anything like that. They call it f of x. Right, the x values, to find the next x value along, we just take the previous x value plus however h is. Okay, where h is a set amount. So that tells you how to work out the next y coordinate and how to work out the next x coordinate. And as I've already mentioned, but it's worth putting down in your notes, that the accuracy of the Euler step-by-step method can be improved if you reduce those step sizes. So if the step size, let's say, is 0.2, reducing it down to 0.1 improves Euler's step-by-step method. But the more you reduce it down, the more difficult all the number crunching becomes. Okay, pause, get down what you need. Okay, so this bit's going to look exactly the same, but there's one subtle difference. Sometimes when you have differential equations, you might have some function that consists of both x's and y's in it. I'll give you an example of an equation that's got x's and y's in. Something like a circle equation, x squared plus y squared equals 4, for example, is a function that's got x's and y's in. Whereas what you're used to seeing is y equals x squared plus 3x plus 2, y equals a function of x. But you can get differential equations where the actual answer you get has x's and y values in. Now, if that's the case, there is some subtle differences with the formula that's worth pointing out. So you're still given that initial starting value. Okay, the only difference you would have is your gradient function would have x's and y's in. So the starting value is the same. The h value will still be given to you, but this is the only difference you're really going to find. To find that new y value, the next y value along, it is the previous y value plus h with the x and the y value. So both that value and that value will be put into the gradient function. Before, it was just the x value that you put into it. But in this case, and you'll see an example of this in a minute, you put both the x's and the y values in to get the gradient. Once you've done that, you've got your gradient, times by your h, add your previous y, out pops your new y. X, exactly the same. You just add the h value to the previous one. Okay, both of those formulas, you can see it there, are in that formula book. You don't need to learn them off by heart, but you do have to have a vague idea of how they work, okay, which I've gone through about going traveling in the direction of the gradient and being able to plot the next number. So you do have to have an idea of how it works, but on a whole, it will just be about using those formulas. Okay, so in your notebooks, I know it's quite long-winded, but it's worth making sure that you've got it down nice and clear, is that exam question. So I'm not going to read it all out for you, but just looking at some of the key bits of information, you can really tell it's going to be the Euler formula, not the fact they actually mention his name in it, but also the fact that you've got a differential equation here, okay, and it's saying to you, we've got a differential equation which is a function of x and y, And now you can see the sort of thing I was referring to. Look at that equation just there. You've got the gradient function is worked out by doing 2 plots of cos x divided by y squared minus 1. So you have a gradient function, or a first order derivative in this case, first order differential equation, that has both x's and y's in it. We've got a starting position, good, and then it's telling you to use the Euler formula, which is a bit odd seeing as it's given to you in the formula books, but I'll talk a little bit about that later on, about why it's quite common for the examiners to give you the Euler formula written down again. Giving us a h value, so we know the step size, and what we want to do is we want to find an approximation for the y value when x equals 0.2. So this is just slightly different notation as well that's worth noting. It's telling you what's the y value at 0.2. It doesn't use f because the f function is attached to the gradient, attached to the differential equation. Look at the notation there. The function yx. We don't know what the y function is. We're never going to know what the y function is, but this is telling us we can estimate a y for any x value. Okay, so make sure you've written it all down. Pause. Feel free to have a go yourself first, and we will have a look through the model solution. Okay, so let's see how far you got then. So the value at x0, y0, so the very first value, just going to write it down so I understand this notation. When x equals 0, the y value equals 3. Okay, so when x equals 0, y equals 3. That's what it's saying there, 0, 3. But I also got the gradient at 0, 3. Okay, so the initial gradient. Now the initial gradient is me chucking in 0 and 3 into that. And that's going to give me this part of the formula. All right, the f xr yr part. In this case, it will be x0, y0. So I know it's going to be 3/8. Okay. Euler's formula I'm using, it's written there. It's written in the formula books. I can work out the next y value by doing the previous y value, which was 3, plus my h value, which is the step size of 0.1, times by the gradient at that previous point. All right, so I know which direction it was traveling in. So y1, because I've got y0, I'm looking at the next one up, it's an iterative method, is 0.1 times the gradient at x0, y0. Now I've done that work already, so I can see it's just going to be 3, which is the previous y value. There we go. Previous y value plus 0.1, which is the h size, times by the gradient at that previous point, x equals 0, y equals 3. So there we go. Work all that out. There's my y value, 3.0375. So roughly speaking, that would be the value of y when x equaled 0.1. Okay, because it starts off at 0, it's going up in 1 each time. So that's what I'm going to put now. The value of x1 is 0.1 plus, 0.1x, 3.0375 for the y. And I can just do the same bit of work. So the first thing I want to do is work out the gradient at this point. So I'm getting my gradient equation, my first order derivative, and I put in 0.1, I put in 3.0375. Once I've done that, I can then get the answer to it. So there we go. I know what the gradient is at that next point along. I know it's roughly going up in about 0.36. That's the rough direction it's traveling in. Right, so got that. I'm going to use the Euler formula again, but this time for y 0.2. Okay, and I get y2 equals y1 plus 0.1 blah, 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 blah. I put my numbers in. So there's my y1 from there, plus 0.1, which is the step size, times by the previous gradient at 0.1, which is there. Once I do that, there we go, 3.07 is going to be my y2, or more importantly, the y value when x equals 0.2. Okay, so what I'd like to do, have a quick go at the exercise on 13C, and when you've had a go at a few of those, we're going to move on to improving Euler's formula. Okay, so just want to quick look at an example of why sometimes it's more appropriate to improve Euler's formula rather than just using the same formula that's in the formula book. So we noticed that in that previous example, when we looked at the first approximation, it was an overestimation. And then the problem was, once that was an overestimation, the next value along overestimated again. And so it compounded on the error. And the reason for that is because the curve was in a sort of concave shape. And the error just keeps going. Okay, and yes, it does come back round, it does follow the general shape, but by the time it does actually start to come back round, we've noticed that this error is just compounded over and over again. So that's what the problem was with that Euler step-by-step method. Now, yes, we could improve it by reducing the steps, but sometimes you can reduce it by improving the actual formula itself. So for example, okay, if I look at a different way to improve that formula, so a different way of doing it. If instead of work out this y2 value, not the y1, but the y2 value. So instead of working out that y2 value, if I'd just done something slightly different, because last time I would have taken the previous y1 plus my h value, which was 0.2, times the gradient at that point. That's how I would have worked it out. So what I'm going to do is I'm going to change the formula. I've realised there's an improvement. If instead of using the y1 at that point, okay, what I'm going to do is I'm going to use y0 at that point. And I'm going to, instead of adding just one lot of that gradient there, I'm going to add two lots of the previous gradient. So from that point, instead of going up to there, what I'm going to do is I'm just going to do that point plus two amounts of this gradient. Alright, so I've worked out the gradient there and I've added it on. So look at the difference, the subtle difference in the formula. To get my y2, I need to work out my y0, that's fine, that's the starting position, plus two lots of the gradient at x1 and y1. So they've changed the formula around. Alright, so instead of working out two lots, doing that gradient plus that gradient, they're saying it's more effective, it's better in this graph to just work out the gradient on the second section and just do that twice, okay, rather than doing the first gradient and then the second gradient. All right, so that's an improvement. And what does it do? It takes you a lot closer to the curve. Now, if I repeat that again, right, so to get the next value along, notice I'm skipping a value out. There was no cross here. So to get the next value along, all right, in other words, which will be this value just here, which was y4, but now it's going to be my new sort of y value. It will still be y4. So what am I going to do? I will do that value plus two lots of this gradient. So once I've calculated this second gradient, I ignore that gradient completely and I use that gradient twice. All right, so it would be from there, I'll be looking at adding two lots of this gradient on and it takes me to there. Okay, we'll look at one more then for this improved method. So from there, normally I would have done gradient, just done it once, gradient, just done it once, but this time I'm looking at the gradient, ignoring the first one along, looking at the second one and doing that twice. So there you go, 1, 2, gives you that value. And you notice that this improved formula gets you a lot closer. The actual shape of the graph is a bit more chunky, but the actual values themselves are a lot closer approximate values for the y values. All right, so that's what makes it an improved Euler method. All right, so grab your notebooks then, please. There's not one way of doing it. That method that I just showed you was the one that's in your formula books. Okay, the one that's in your formula books looks like this. So for any gradient function, so first order derivative, looks like that, with a small step size h, which is given to you, and an initial value. All looks exactly the same as the Euler step-by-step method. Okay, in fact, it still is an Euler step-by-step method. It's just got a different formula, an improved formula up. Right, then I could do this. To work out y value plus 1, so the next y value along, it is going to be the previous y value, so not the one just before it, but the one before that, plus 2 lots of the gradient of the previous y value. So I need to start there. I need to work out the gradient of the next one. Okay. And then what I need to do is I need to add the gradient of the next one along and add it on twice. Okay. That formula is given to you in the formula book. So they give you that improved formula. So if they did say to you in that exam, we want you to use the improved formula, you'd have to go to your formula books. You'd have to use this formula just here. Okay. And then you could work out, if I wanted to work out, for example, y2, I'd have to do y0 plus 2 lots h times the gradient at y1. Okay. So once I've got that then, I'm just writing down there the other formula that's written in your formula books, which is if your gradient function, if your first order derivative is just in terms of x. Now look, they're pretty much exactly the same. Everything's exactly the same, except instead of doing x and then y, x and y, they just have the x in there. But it does depend on what your equation looks like. So if it's something like dy over dx equals x squared, that's one of these. If it's dy over dx equals sine x over y, it's one of these. Okay, if you've got x and y in your equation, then use this one. Okay, as I just said a minute ago, there is lots of different Euler methods. Someone could come along and say, this is a way of improving your Euler step-by-step method. Use this formula. And what we'll do is we'll look at an example of one of those. So just pause if you still need to take any notes down. Okay, so last question. Again, I know it's a bit of a beast, but it's worth putting it down in your notebooks. Nice and neat. And we'll just have a look through and just see some of the key differences. You can see from the first part that we could just be asking you the same question as what you've just been doing. You've got a differential equation, you've got a function of y, which I don't know, so the y value in x is whatever I like. The f of x is our gradient function, I need to be aware of that. So y ln x plus 2y is the gradient, is the differential equation for this function just here. The one point I do know is y equals 3 when x equals 2. Okay, so when x equals 2, y equals 3. So I do know that point just there. What I need to do now is I need to work out Euler step by step. But instead of using the one in the formula book, I'm going to use an improved one. And this is why it's quite common for the examiners to give you the Euler formula, even though you're given it in the formula book, because they want to make sure that you are using the correct formula, because there are lots of alternatives out there. So in this formula, the formula basically says, if I want the next y value along, I use the previous y value plus a half of k1 plus k2. So a very different looking formula just there. There's no h value in this formula, but I've got these extra k1 and k2 that I need to be thinking about. So what's k1? Well, k1 is the same as what I've dealt with already. It's the h value, which is given to us in the formula. There it goes. H is 0.1, the step size, times by the gradient at whatever R value I'm dealing with. So if I'm dealing with, I want y, let's say y3, that's going to be y2, and so therefore this is going to be x2, y2. Okay. What's k2? Well, k2 you work out by doing h again, so 0.1 times the gradient. So times the gradient of the previous one plus the extra h. So I'm going to have to add an extra h to my x, and y is going to be plus the extra k1, whatever this was. Okay, I think the best thing to do is to just try putting some numbers into this to see if we can get it to work, because it looks like a bit of a nightmare. Okay, so to find the value of the improved formula, first thing I'm going to have to do is work out k1 and k2. So there's no point in trying to just put it into here, because I need to know what k1 and k2 are. So I'm starting off with that very first value, x0, y0. That's going to get me my first k value. All right, so I'm just starting off with the very first values. So to work out k1, I'm doing 0.1, which is my h value, there you go, fill that in, times by the function, the gradient function for my first two x and y values. Now I know that y is 3 when x is 2. Okay, and that's what's coming here. Look, I've just basically put in 3 ln 2 plus 6. 3 ln 2 for x plus 2 times 3 is 6. So I've working out k1, I do h times the gradient, the differential equation for x naught y naught. There we go, 0.62383. Right, so that's k1 worked out. I'm going to work out k2 as well. So k2 says this. I do h, then I use the differential equation just there. And the two values I'm going to put in, well, the x value I put in will be x naught, which is 2, plus h, so that's 0.1. So I'm going to use 2.1 for my x value. And the y value would be y naught, which is 3, plus k1. So it's going to be 3.623. So I'm just substituting both those in and make sure I know which ones I'm actually using. So there we go, 2.1, which is the 2 plus 0.1, and 3.623, because that's going to be y naught, which was 3, plus the previous k value. Right, okay, now I've got my head around that. Let's just work out what this is. 2.1 in for x, 3.623 for y. So there you go, substitute it in. There's a y value ln x value plus 2 lots of the y value. And what does I get? 0.80997. Right, so now I've finally got my k1 and my k2, I can then look at the next y value along. So my next y value, luckily I only have to do this once, because I've got 2, they want 2.1, so they only want one iteration of it. It's going to be my y naught, that's my first y value, which is 3, plus a half lots of k1, so there's k1, plus k2. So there we go. So I've got to add those two together, half it, add it on to 3. There you go, 3 plus a half of that. So there we go. My approximate y value when x equals 2.1 would be 3.7. So for this function just here, when x equals 2.1, that y value is roughly 3.716. Okay, pause there if you need more time to put in your notebook. Okay, so what I'd like you to do, please, is I'd like you to have a look at exercise 13D. So there's lots of different improvements on the Euler method, and it's worth making sure that you practice a few of those because they can ask you some weird ones like you just saw in that exam. So it's making sure that you've already got a heads up for it.